Hi girls, so I know I set you this on Thursday to do on Dr. Frost, but I just wanted to have another go at it today because it does get quite difficult. I'm not actually, I'm off timetable today. I'm in a meeting all day, so not around to do a lesson. But I did want you to have another go at this because it can be really difficult, and it is something that you need to be able to do at IGCSE. It's something that's difficult at GCSE anyway. But again, if we get a head start on it now, then when it comes up again in year 10 or 11, you've been exposed to it, you've already had a go, and you have an idea of how it kind of works. So these are tree diagrams with no replacement. So you're picking a counter out of the bag and you're not replacing it, which means the second time you pick something out of the bag, or if you pick a second counter, your probabilities have changed because there's one less counter in the bag. And depending on what colour that first counter was, changes the probabilities the second time around. So your tree diagram is showing you the different combinations of things that can happen. It doesn't mean they're all happening simultaneously. They're not all happening at the same time. You're kind of imagining that, well, what happens if I pick a red counter? What happens if I pick a blue counter? And so on. But this is red and blue counters. You've got 3 red and 4 blue counters in a bag. Counter is taken out, its colour is noted and then replaced in the bag. A second counter is then taken out. Use a tree diagram to work out the probability that exactly we wanted it to be not replaced. I think I've cut off half of the question, so we're going to ignore that and say not replaced because that's what I wanted to show you or wanted to go through with you. So counter is taken out, its colour noted and not replaced in the bag. You are keeping that counter, I don't know, somewhere else, in your hand, in your pocket, on the table. It's not going back in the bag with the rest of the counters. So to start off with, the first time you pick a counter, so the first counter you pick out of the bag, you've got 3 red and 4 blue. That's 7 counters altogether. So the probability that it's red is 3 out of 7, and the probability that it's blue is 4 out of 7. That's nice and straightforward. But the second time for the second counter that you pick out of the bag, the probabilities have now changed because there's one less counter on the bag, and we have to look at what happens if the first counter you picked was red. How does that affect the probabilities? And what happens if the first counter you picked was blue, and how does that affect the probabilities? Because they will have slightly different impacts. So the tree diagram is showing us what happens if we pick a red counter. We look at red first. So if we pick a red counter out of the bag, that means there's now only 6 counters left because you've taken one, you're not putting it back, so there's only 6 counters left in the bag. So both of these probabilities are going to be out of 6. Okay, and if the first counter you chose was red, that means there's now only 2 red counters out of the original 3 left in the bag. So the probability that the second counter is red, if the first counter is red, is 2 over 6. The blue counters haven't changed. There's still 4 blue counters in the bag. They're just out of 6 counters altogether because you've taken one out. Okay, I hope that makes sense. Now we look at what happened if the first counter you picked was blue. Now, what you have to remember is these two things are not happening at the same time. You've picked one counter. We're first looking what happens if that counter was red, and we have a look at how that affects the probabilities, and then we ignore that and we go back to the beginning and we say, okay, well, we've picked one counter and it's blue this time. How does that affect the probability for the second counter? Okay, so we're kind of starting from scratch again. So we've picked one blue counter out, meaning there's 6 counters left in the bag because you've taken one out and you kept it, you haven't replaced it. But this time the counter was blue, so that means there's still 3 red counters left in the bag because this time we haven't picked a red counter first, we've picked a blue counter. And now there's only 3 blue counters left because we've taken one of them out. So there's only 3 left out of the original 4. So you can see that the different parts of the tree diagram have different probabilities this time. So these 2 probabilities are different to these 2. They're all out of 6, because each time we're only taking one to start with. So we're left with 6 counters for the second counter, the second, I don't know how to put that into words. We're only left with 6 counters to choose from on our second go. But you can see that they differ slightly depending on whether the first one was red or the first one was blue. It changes the probability slightly. Now we want to work out the probability that exactly one of the 2 counters is red. So we do the outcomes and the combined probabilities in the same way. So we could pick a red and a red. These are our outcomes. We could pick a red and a red. We could pick a red and a blue. We could pick a blue and a red. Or we could pick a blue and a blue. The probabilities of those things happen, again, come from multiplying together along the branches. So the probability of red is 3 over 7 multiplied by 2 over 6, which is 6 over 42. I'm not going to simplify anything at this point. I'm just going to leave it as it is. The probability of red-blue is 3 over 7 multiplied by 4 over 6. Which is 12 over 42. Blue then red is 4 over 7 multiplied by 3 over 6, which is 12 over 42 again. And then the last one, it's still 4 over 7 times 3 over 6 is still 12 over 42. We're interested in the probability that exactly one of the counters is red. These 2 outcomes have exactly one counter being red. We've got red then blue and blue then red. So that means we have to add these 2 probabilities together to work out the total probability. So to answer this, the probability 1 red is equal to 12 over 42 plus 12 over 42. That's a 2, which is 24 over 42. And that's why I didn't simplify anything at that, when I worked those out either, because we want to add them up. We need the denominators to be the same. So if we don't do any simplifying, that makes that a lot easier. So 24 over 42, we're going to simplify now, gives us 4 over 7 because they both divide by 6. And that's that question. So we've had a look at the tree diagram. We've looked at how the initial counter picked out of the bag affects the second counter, and then we've used the tree diagram to calculate the probability of a combination the same way as we were doing last week. Okay, I've got one more example for us to look at. We've got Ron again. I love Ron. So this time 2 of these number cards are picked at random. So we've got the numbers 1 to 5 on cards. What is the probability at least one of them is even? Now Ron says that there are 5 possible outcomes for the first card and 4 for the second card. So we need to draw a tree diagram with 20 branches. Do we agree with Ron? And hopefully we can see that Ron's wrong, because yes, there's 5 cards to choose from, and once we've picked one, there's only going to be 4. But we're not looking at the individual numbers. We're not interested in the individual numbers. We're interested in whether it's even or not even or odd. So actually our tree diagram only needs to have even and odd on it, which is what I've drawn on the next slide. Okay, so we don't agree with Ron. We don't need to put all 5 cards and then 4 on the second pick. We just need to put even and odd. I probably should have put even at the top because that's what we're interested in, but never mind, it's fine. So the probability that at least one of them is even. On the first pick, we've got 5 cards. 2 of them are even, so this would be 2 out of 5, and 3 of them are odd, so 3 out of 5. Now again, we've taken a card. We are not replacing it. That's important actually. This often confuses people. 2 of the number cards are picked at random. Now, if you're picking 2, that means you're taking one and you're not putting it back, and then you're taking another one straight away. Don't get confused and put kind of extra branches on and things. We're taking 2 cards, but we're doing them one at a time, for the sake of drawing a tree diagram. So this is the first card. Oh, I still got the highlighter on. So this is the first card and this is the second card because we're picking 2 in total. But because it says we're just picking 2, we are not replacing them. We are not putting that first card back. So once we've picked 1, we've only got 4 left to choose from. So we've taken 1 card. If the first one is odd, we've got 4 cards left because we've taken 1 of the 5 away. And we've taken 1 of the odd cards, which means we're only left with 2 odd cards. And the 2 even ones are still there. That's what happens if the first card we pick is odd. Now we ignore that and we go back to the beginning and we think, okay, well, what if the first card we picked was even? Then, again, we're left with 4 cards because we've taken 1 of them away. But this time, the odd cards have stayed the same. We haven't taken any odd cards left. So we've got 3 out of 4 odd cards and we've only got 1 even card left because we've taken 1 of them already. And then we can work out the outcomes and the probabilities that we're interested in. So there isn't actually a question here, but let's have a look at the different outcomes. So we could get odd, odd, we could get odd, even, we could get even, odd, or we could get even, even. And again, to work out those probabilities, we multiply along the branches. So odd, odd would be 3 over 5 multiplied by 2 over 4, which would be 6 out of 20. Odd, even would be 3 over 5 multiplied by 2 over 4 again, so also 6 out of 20. Even then odd would be 2 over 5 multiplied by 3 over 4, so also 6 out of 20. And then the last one is 2 over 5 multiplied by 1 over 4, which is 2 out of 20. If we added those up, 6 add 6 add 6 add 2 makes 20. So we know we've done that correctly because it makes 1 altogether at the end. Let's come up with a probability then. So the probability that we get at least 1 even. That is the question. It's here. I'm not reading it properly. What is the probability that at least one of them is even? So looking at the outcomes, we are interested in anything that has an even in it. So odd, even, odd, and the 2 evens. They all have at least 1 card that is even. So to work that probability out, we add those 3 ones up together. So we do 6 over 20 plus 6 over 20 plus 2 over 20 is 6 add 6 is 14, 6 add 6 is 12, add 2 is 14. So 14 over 20, which is 7 over 10 if we simplify it by dividing by 2. And that's it. So I did 2 examples. Please use these to help you answer the questions on the Google Slides. They'll all be very similar. But like I say, I understand this is a difficult topic, but the more comfortable and confident you are answering these questions now, the easier you're going to find them when they come up again during your IGCSE, because that's what we're preparing you for now. Is starting the IGCSE course in September. Okay. So yeah, have a go at the task. Please submit it by the end of the lesson. And have a lovely day. Thank you, girls.